In the previous video, we had an introduction to just regular binary trees, but today we're going to be talking about sort of a very special type of binary tree that we tend to use a lot in computer science. So remember that a binary tree nodes contain some amount of data, just like a linked list node, and they link to up to two other nodes, right? So they have a left and a right link that comes out of them. And it ends when the nodes have only next pointers. So we call leaves the nodes that only have null next pointers, right? We refer to the top of the tree as the root, and all of the other nodes that may or may not have between 1 and 2 children, we call them internal nodes, right? And remember also that we talked at some point about binary search. So binary search, given a sorted array and a search item, determines if the search item is equal to... So it runs an algorithm where it starts by looking at the element in the middle of our sorted array. If that element is equal to the thing we're searching for, it returns true. If it's not, and it's smaller, it searches in the left part of the array, right? Because it's sorted and it's smaller, so it has to be on the left if it exists. So it goes to the middle of that array, asks whether it's equal to the middle or not. Here it's not, right? So it looks at the right side of the remaining part of that array and tells whether or not it's there, right? In this way, it's always splitting the array in half, and that's only because we have a sorted array. Right? So what if we brought the same idea that we use for binary search into the tree space? So imagine now that we have basically a sorted tree. So imagine that your root is the middle node. So your root always has some value, and all of the things on the left child have values that are smaller, just like the left half of the array contained all the elements that were smaller. And all the stuff in your right child has values that are greater, right? So in this way, so a balanced binary search tree would actually provide the same running times as binary search on a sorted array, right? It's the same idea. You're splitting the amount of stuff you have to do in half, right? Sometimes it might find something faster, though, which is actually something else. And we'll see later on in the next video, actually, that when you add an element to a sorted array, it can take... so we know that adding something to a sorted array, sometimes you have to resort, whereas adding to a balanced binary tree can be much faster. So I mentioned that a balanced tree, so I mentioned that terminology on the last slide, but a balanced tree is a tree where the difference in height between the left and the right subtree is at most 1. So if we have, and in addition, the left and right subtrees are balanced. So real quickly, what is a subtree? So a subtree, if we have some binary tree, right? It's boop, 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 right? A subtree is a tree induced by basically disconnecting one of these internal nodes. So if we got rid of that, there's still this tree here, and we call that a subtree. So a balanced tree is one where the left subtree, right? So we have our node, our root, and it has some tree, and maybe it's that, right? This tree has some height, h. And the induced subtree, so the subtree on the left and the subtree on the right, each also have a height. So what we're saying is the difference in height of the left and right subtrees is at most 1, and the left and right subtrees are both balanced, right? So it's a recursive definition of what we mean by a balanced tree. So balanced trees actually provide us a much faster search time, as we'll see when we look at the search algorithm. So given that we do have a binary search tree, how do we find an element in that tree, right? Just like we wanted to do with binary search, can we find an element in the tree? So starting with what we're going to do is we're going to start with the root of our search tree as our current node, and we're going to check to see if the current node matches the search, just like we checked the middle of our subarray to see if it matched. If it does match, then we found the element we're looking for. Right? If the value is bigger, right? If the value we're looking for, if the value at the current node is bigger, meaning the search thing is smaller, that means that because of the way we've constructed the binary search tree, then if the value exists, it has to be somewhere in the left subtree, right? Because its value is smaller than the node that we're looking at. Similarly, if the value is bigger than the current node, it has to be in the right subtree. And if the subtree we need to look at is null, right? If it's a null pointer, then that node can't exist, right? Because it should be to the, say it's bigger than my value, but my right pointer is null, then it should be there somewhere, but it's not, so I return false. So let's trace a couple examples real quick. Let's go through the same example that we had on the slides just a bit earlier, where we're looking for the value 7. Right? So the first thing we do, we start with our current node being, our current node is the root, and we ask, is 7 equal to 8? Well, 7's not equal to 8, so I'm going to need to pass off this to either my left or right child. And I say, well, the thing we're looking for is smaller than my current value, so it must be in this left subtree, right? So I'm basically going to make a recursive call on this node 3. So that's what we do. We move to the recursive call on the node 3, and these we're supposed to build in, but 3 is not equal to 7, so we know we're going to have to make a recursive call. And 3 is less than 7, so we know that recursive call should be made to the right. Right? If it exists, it has to be in the subtree that's here. I don't necessarily know how big that subtree is, I just know it exists. Right? So we do that, and now the current node is 7, and it turns out 7 is equal to our search, so we return true. Right? So we recursed all the way down, and we got to the node that we were looking for, so we can return true. That value is in our tree. So let's try another one. Let's try 13. So looking at this as a human, again, we can see 13 doesn't exist in this list. But let's see what the algorithm is going to do, right? Because the algorithm, right now, all we know is the current node. We need to validate the 13th not the list. So the first thing we ask is 8 equal to 13? Well, 8's not equal to 13, and 8 is less than 13, so we know if 13 exists, it needs to be in the subtree to the right. So we make a recursive call on 15, and we ask, is 15 equal to 13? Well, 15's not equal to 13, and actually 15 is bigger than 13, so it must be in our left child. So we make a recursive call on 12. Well, 12's not equal to 13, and 12 is less than 13, so we need to make a recursive call on the left child. But now the left child is null. So if the left child is null, is 13 anywhere in our tree? If it was here, it would have to be to our left. Because it's greater than 8, less than 15, and greater than 12, so it should be over here somewhere. But it's not there, which means we can return false and be okay with it. Right? So we'll see in the next video how to add things and how to build these binary search trees, and how to keep them nice and balanced.